If x and y are random variables, then you should know what we mean by the conditional expectation of y, given that we know that the random variable took the value lowercase x. For a specific value of x, this is just a number. Since we can use any x in the range of the random variable x, we can also view this expression as a function of x. The conditional expectation of y given x with no equal to sign, that is then defined as a random variable, and specifically the random variable you get when you compose g with x. So we will extend the idea of a conditional expectation to the case when we have random vectors. We'll begin by allowing this to be a vector while keeping y as a random variable. And then in a second step, we allow y as well to be a random vector. But let's begin with the case when y is a random variable and x is a random vector. So based on one and the same experiment, we have defined n plus 1 random variables. N of them are collected into the random vector x, and one of them is given the name y. We have a joint density yx, which depends on a single variable y and n variables x. So this is a function of n plus 1 variables. By integrating away the y random variable, we can get the marginal of x, which is a function of n variables. And from this, we can get the conditional density of y given x, which is the joint divided by the marginal of x. This is again a function of n plus 1 variables. That's all we need to define the conditional expectation when we condition on a random vector. So the conditional expectation of y, given that this random vector took a specific value, in this case a specific vector, that means that I know the outcome of every random variable in the x random vector. I know that x1 came out to be x1 and so on to xn came out to be xn. The conditional expectation of y, given this information, which is now almost complete, we know the outcome of n out of the n plus 1 random variables. Well, that's going to be a single integral y times the conditional PDF of y given x. The conditional density, remember, is a function of all the x variable as well as of the y variable. By doing the integral, we lose the y variable. So this will be a function of only the x variables, all n of them. So think about it like this. We feed an n by 1 vector into the conditional expectation, and it will return a number. So this conditional expectation is a function of x, where g has its domain Rn. We need to feed n numbers into it, all the outcome of the n random variables x, and the codomain, it will return a real number. So this thing then, y given x, is defined just like before, simply as g of x, a composition of the g function with the x random vector. Since g returns real numbers, this is a random variable, not a random vector. So let's move on to the next step when we do conditional expectation of a random vector with respect to another random vector. So now I have an experiment on which I have defined m plus n random variables. M of them are collected in y and n of them are collected in x. It's completely up to me to decide which ones go into y and which ones go into x. So based on how we define the unconditional expected value of y, that's simply defined as the expected value of y1 to the expected value of ym. This becomes an m by 1 vector. the conditional expectation of y, given that I know the outcome of each random variable in x. So this is x. X here is an n by 1 vector of constants. This is defined very similar. It is defined as the conditional expectation of y1 given x equal to x down to the expected value of ym given x equal to x. So each of these numbers is a conditional expectation of a random variable conditionally on a random vector. So that goes back then to the previous definition. So each of these conditional expectations, say yj given x equal to x, we integrate over rm yj times the conditional density y given x dy. This dy is really dy1 dym. The conditional PDF contains all the y and the x variables, but since we integrate away all the y variables, this is just a function of x. So the conditional expectation of the random vector y conditionally on the random vector x is g1 of x to gm of x, which we can combine into one function, g of x, where g is now a function from Rn, we feed n variables to it, into Rm, it returns m numbers. And we finally define ey given x simply as g of x, which is now an m by 1 random vector. One of the key things to remember is that in this expression, y given x, this will always become a random variable or a random vector. Its dimension will always be the same as the dimension of y. If y is a random variable, the conditional expectation is a random variable. If y is a random vector, m by 1, the conditional expectation is a random vector. The dimension of this does not in any way depend on the dimension of x. We had 4 very important results for the expected value and the variance of a linear function of a random variable. If c is an n by 1 vector of constant, then the expected value of this linear function, I can take this c outside, so it's c prime e of x. The variance of this linear function, I need to take c once here and once here. It's c prime variance of x times c. If A is an m by n matrix, then the expected value of ax, take out the a, is a expected value of x. The variance of ax, take a both sides and transpose it when it goes to the right. So it's a variance of x, a transpose. We have seen previously that these results work for conditional expectations and conditional variances as well when we deal with random variables, and they will also work in the case when we deal with random vectors. So these are the results. The conditional expectation of this linear function c prime y given x. Just take the c prime outside. Just to confirm dimensions here, c prime y is a scalar 1 by 1. So this conditional expectation is a random variable. This conditional expectation is a random vector. Its dimension is the same as that of y. So it's an m by 1 random vector. And since we do c prime this random vector, the right hand side is a linear function of the random variables in this random vector. So this whole thing comes out to be a random variable itself. The conditional variance works exactly as the unconditional one. You take c prime to the left and you take it to the right and transpose it. C prime variance of y given x times c. Again, both sides are random variables. In this case, the variance of y conditionally on x, since y is an m by 1 vector, this is an m by m matrix of random variables, and the whole thing will become a random variable. If A is a k by m matrix of constants, then the conditional expectation works the same. We can take this A outside. So it's A expected value of y given x. In this case, A times y is k by 1. So both sides are random vectors of dimension k by 1. The conditional variance, take out A here, take it out here and prime it. In this case, both sides are k by k matrices of random variables. This is an m by m matrix of random variables. Finally, we also had the laws of total expectation and total variance. The first one we also called the law of iterated expectations. These can be extended when we deal with random vectors as well, and the formula look identical. The law of iterated expectation, or the law of total expectation, the law of total variance. Just to confirm the dimensions here, the expected value of y given x. This is a random vector of dimension m by 1, the same as the dimension of y. So both sides of this expression are m by 1 vectors of constants. Variance of y is an m by m matrix of constants. Y is m by 1, so the variance of y conditionally on x will be m by m, but a matrix of random variables. When we take the expected value of that, it goes into a matrix of constants. This is an m by 1 random vector. When we take the variance of an m by 1 random vector, it goes into an m by m matrix of constants. Dimensions are fine. All three terms are m by m matrices of constants.